All right, so today we will go through the algorithm for hashing the SHA-1 algorithm. Okay, so last time I went through this one a little bit, but today we will go into the details for how to implement that. And also I will have some hands-on exercises to show you step by step for how the hashing algorithm works. Okay, so the SHA-1 algorithm has 4 steps as follow. And by the way, there are quite some algorithms for hashing, like MD, right? MD2, MD4, MD5, but they are not well secured like the SHA. So that's why SHA, especially the current one, SHA 512, is the most common algorithm for the blockchains and also for digital coins. Of course, it's used for network securities as well. All right. So the 4 steps. First, we will try to append some bits into the message. Okay? The idea of that is that we want to break the message into blocks with 512 bits each, right? So that said, if we have a message and that is not a multiple of 512, then we have to append something uh, like zero, etc. Okay, and then we also want to take into account the length of the message as some information that will help us to secure the hashing value or the digest more. Yeah. And then after that, we will try to initialize a hash buffer and process through the message block by block. And finally, we output the final digest that has 160 bits. Okay, so the idea is very simple. Okay? We just want to uh, say hash the values or the bits of the message we have. Yes. So generally speaking, we have the following situation. The original message, as I mentioned before, may not be a multiple of 512 bits. Okay, so some message be short and some will be long. So that's why we need to pad some values. Usually we pad 1 and then after that 0. Okay, and we also add the length of the original message as a number using 64 bits. Yeah. So that's why we break the message into, say, blocks. So here for SHA-1, n bit is the 512. Okay, and SHA-2 is 1024. Okay, and then we initialize the digest or the hash value by some initial values. So initial values, the idea is very simple. We try to have some ones and some zero in the hash value. Okay? So we don't want to initialize the initial hash value with just only 0 or just only 1. In that situation, it's easier for cracking the message or the hashing algorithm. Okay? So that's why we initialize the hash value with some, we can choose random generated numbers, but usually we have some specified initial values. I will show you a little bit later, right? And then we use the initial values for the hash, take into account the first block, okay? And then shuffle the bits a little bit, yeah, having the new initial values for the hash that take into account the second block, right, etc. Until we have the last one, and the last one will be the hashed or the digest. Okay, so again, the idea is very simple. Okay, so the key point is that what kind of manipulation we have for the bits, so that at the end, okay, when we have the hash value, it's secured, meaning if we have the hash value, it's very hard to find what is the original message, so that after we hash it, we have the same value. Okay, so that is what we call the pre-image attack that I mentioned last time. Okay, and then the manipulation is pretty simple. Okay, so here we have one block. Okay, and then the initialized value we have here, and we break it into smaller works. Okay, so this one you have 160. Then here you have 5 works, right? Each work has 32 bits. Okay. And then we repeat the process 80 times, meaning that we shuffle the values of the bit 80 times. Why 80? Because we have some statistics saying that 80 would be a very strong hash value, right? So why not 20? Yeah, 20 will work, but it's easier to crack the hash algorithm. Okay, more than 80, that's fine, but the algorithm will work longer, right? And you will see that here we need to have a secure and efficient algorithm. All right, and starting from some initial values, how do we manipulate the bits? So we have initial value for A, B, C, D, and E. Each of them has 32 bits. Yeah? The initial values, as I mentioned before, has a balanced number of 1 and 0 in all of the bits. And then after that, we will do it for each block, right? And after each block, A of the previous one will become B of the next one, right? And then A will rotate to the left 5 bits. Okay, it's the rotation. Yeah. So meaning that we shift to the left 5 bits, and of course it's a rounded one. So the extra bit, the 5 bit in the front will be brought to the end. So that's why we have the rotation shift, left shifting, right? And then after that, it will be mixed with the E, right? And then mixed with the value of the message, right? Here is the value of the message. And here is the constant value. Constant value, we can control that. So that's why we can have our own hashing algorithm, okay? By providing the values for A, B, C, and D, and also providing the value of K, then we have a brand new hashing algorithm. Okay? So you can see that we have a lot of digital coins like FTX, right? Very famous now. Bitcoins or Ethereum, right? Each of them will have their own hashing. They don't choose the standard one because they can control what they have. Yeah. Okay. So how do we mix or say shuffle the values? Is called the F function. Okay, the F function is here. So you can see here, right? So we have 3 works, B, C, and D, and then we mix them together using a function F. Okay, what does it mean with F? It's very simple. F is just here. When T is between 0 and 19, we have B and C or not D and D. Okay, why that function? Because we want to do some, say, mixing of the bits, right? So as far as the different functions it will work. And then when t is from 20 to 39, we have XOR B, XOR C, XOR D. Okay. Similarly, for t from 60 to 79, we have this. Okay. And then the constant value, we use this. I will show you how these numbers look like when we have a binary value. Okay. So we have the different constant value for different rounds of processing. Okay. All right. And then the initial values for the hash are here. Okay. We have the first one, second one, third one, right? Okay, so this one I will show you in binary, so you have some ideas about why we choose this. But as I mentioned before, each platform has their own initial value. And I will show you that what will happen if I have my own, say, initial values for the hashing function. Okay. And then the algorithm is very simple. We do it for every block, right? And then we shuffle them, okay, 80 times, yeah, using the function I just showed you, right? And then finally, we do it for every blocks. And finally, we have the result that is the final buffer. Okay. The algorithm is pretty simple, right? We just have not and all, and then rotation, right? Is it secure? Yes, it's secure because it has been there for 30 years and no one can break the system yet. And then whether or not it's efficient, yeah, it's very efficient. Actually, from here, we can have the complexity. It's big O n, where n is the length of the message, right? In fact, what we see here is that it does the manipulation 80 times, right? So that means that is 80 times n, which is big O n, right? Every message will be repeated 80 times, and then we do it for every blocks. And that said, the algorithm is linear, but is very efficient, okay? And also is very secure because the bit operation here, okay, in order to reverse engineer the algorithm is almost impossible. We have to check for all possibilities. And the problem is that we don't know what is the length of the message because every message is, after we hash it, it has the same 160 bits, right? So the first thing we observe is that if we saw the digest or the hash value, we don't know what is the length of the original message. So that said, we have to perform the exhaustive search for every length, length 1, length 2, length 3, length 4, etc. And that process will take, say, 100 years in order to define what is the original message in order to obtain the hash value we know. All right. Now it's time to have a look at the implementation and also have some hands-on example. Okay. Oops. All right, so here is again the software package Ango that I developed. Okay, and now here is what I have for the blockchain. Okay, so I have the first thing is the hash. Okay, I will close this one. Okay, so I implemented the algorithm, right? The implementation is very similar to what I just showed you. Okay, so first I have the function f, right? The function f here is defined for each value of t. So here we have or, okay, n, and then n and not, right? So from t from 20 to 39, we have b xor c xor d, right? So it's straightforward from the algorithm. Also, we have the bit shift. Okay, we can shift to the left, we can shift to the right. So just have a function for shifting. Okay, in Java and C++, we can use the shift algorithm. I mean the shift function directly, right? Okay, and then we have the circular left shift. Circular shift means that we shift and then we bring the one that we push out of the word to the back of the string. Okay, and now we have the char function. Okay, so the char function, we have step 0, we prepare that. Okay, and then step 1, padding, etc. Okay, it's very straightforward. So now I will use one hands-on example to show you step by step how it works. Okay, so first we have this message ABC, right? Okay, so we want to see what is the hash value for ABC. The hash value is here, right? So it means that we have 160 bits and convert that into hexadecimal, right? So each of this one has 4 bits, right? Okay. Now let's go through the details so we see what we have. All right. So here we have the message is ABC, right? Okay, so we have the message ABC. So ABC will be converted using the ASCII code, right? So we have it into 61, 62, 63, or in decimal number, they are 97, 98, 99. Yeah. So I can have it here. All right. So the first thing we do is to prepare that. All right. We prepare that, and after that we do the padding. Padding means that here you have the message, right? And the length of the message here is not a multiple of 512. Okay, so that's why we want to add some values. Okay, so the values we add at the end is first we add 1 and then we add 0, okay, until we have the whole 512 block. By the end, we will add the length of this message. Okay, the length of this message is 3, right? ABC has the length of 3. This one, ABC has a length of 3. So we will add 3 at the end using 64 bits. Okay, so that is what we have. All right, so we pad that, and you can see that here we have the string converted into binary, right? After that, you can see here is the original string, ending in 1 1. So ending in 1 1. So we append 1 followed by 0. Okay. except the last 64 bits, we will add the length here, right? Okay. The length here, we have the length originally has 3 characters, right? But when we convert that into the binary, it has 24. So we add that one here, 24, right? So 16 plus 8 is 24. All right, so that is what we have. Now the second step means that here is the message after we append to make it a multiple of 512. In fact, it has only one block, right? So that said, we will try to initialize the value of the H, the Y, I mean the H array, and then the K constant. Now, here's what I mentioned before. Here we have the initial value for H of initial value for the hash, right? So the first one is 6745231. That is in hexa value. And if you can see here, when you have it in binary, okay, you have 1 and 0, right? In fact, if you look at the last 4 digits, right? Here you have 000, here you have 001. So basically, here you have 0. If you flip it, it's 0000001, and then the second one, if you flip it, it will be 0010, and then the next one, right? So actually, it goes from 0 to 4, but then we swap the value every times, right? So that is why they have the initial value like this, right? So as far as we have the initial hash value that has the one distributed on the whole string, it will work. Okay, we don't want to have the initial value that has all 0 except 1 here, 1 there. Okay, it will not work. All right, and also that is the reason why people can have their own hashing algorithm, and their hashing function will have a different result when you hash it, right? So that's why if you want to join a platform like Binance, or if you want to join, say, Bitcoin, right, or FTX, they will ask you to have their mining algorithm. And you don't have the source code. They just provide you with the executable file, and then you hash using their algorithm. And then here is where they can control. Okay. Later on, I will show you that if I change my own initial values, I will have my own algorithm for hashing. Okay, the K value also, you can see that they have a, distribution of 1 and 0, okay? So that is why they have the initial value like that, because once you have the 1 distributed equally, then it will work when we try to manipulate the values of the message we want to hash. Okay, so now processing. So we will go through each block, right? And then we, at the beginning, we have A, B, C, D, and E, and initialize with H0, H1, H2, H3, H4, right? And then every time we will try to calculate the new VE, VD, VC, and then VA will be here. A combination of manipulating BCD, right? And then E take into account the message. Okay, W here is the value of the message, right? Everything else will be the variables we have for the program. Okay. All right. So now the result we have is here. So at the beginning, we have A, B, C, D, and E here. And every round, we change the value of A. Beginning is here. And then for the first round, it change to here. And then change here. Right? So the first column is for A. The second column is for B. Third column is for C. Okay. And then D, and then E. All right. So we do it 80 times. And then finally, we have the result is here, all right? The result is here. So we have, okay, this one is the, here we have the X0, X1, X2, X3, right? And then we add this one together, add this two together, add this two together, right? And then we have here the results, okay? 1, 2, 3, 4, 5. Each of them has 32 bits. So if we concatenate them together, then we have a group of 160 bits. And that is the digest or the hash value. Okay? So it's pretty straightforward. So here we just concatenate them together. Then we have the final one is here, right? Okay, so it's 160 bits. All right. So that is about the algorithm and how it works for one particular example. All right. Let's see if we want to have. So you see here that the message has only 3 characters. The hash value or the digest has 160 bits, right? Now, if we have a longer message like this, okay, longer message like this, then the digest or the hash value has the same 160 bits, right? This example has 2 blocks. Okay, let's see what are they. So here we have this one, and you can see that the message is here, right? And when we convert it into decimal number, we have here. When we convert the message into the hexadecimal, all right? So here's what we have. Okay. So first, we pad the message, right? So here is the original message, right? We pad it with 1 followed by 0, except the last 64 bits, we have the length of the message, right? The length of the message is here. Okay, and it has 2 blocks. Okay, the length of the origin message is 448, and then we add 64 bits for the length. It went beyond the 512, so that's why we have to add 1 block of basically 0. So here we have 2 blocks, one with the message here basically, and the other one has most of them 0. Okay, and then we initialize again. We use the same f function for manipulation, right? Not and or only, right? And then the constant k, they are the same. Okay? They're the same. All right. So now you can see here that it has 2 blocks. So it will have to repeat the algorithm twice. Okay. So the W or the message are here, right? Okay. So we have the W. Okay. This one is for the second block. Most of them are 0, except the last one. Okay, here's the second block, right? We have the first block as well. So here's the first block, right? So we have the first block has this value. Okay. This one, when we convert that into decimal, okay. All right. And now we have A, B, C, D, and E initialized. Okay, so after that, it will be here. After the first round, second round, okay. So for the first block, after we finish, here are the H values, okay, and we use this for the second block. The second block are here. Okay, most of them are 0, okay, except the last one. Except the last one. Okay. And then we have A, B, C, and D, which is initialized with the H values we got from the first block. And now we have the values of A, B, C, and D here. Okay, and after we finish, we have the H values, right? And now when we convert that, okay, convert this one into hexa, we have this one. When you concat them together, is the final digest or the hash value of the original message. Okay. So that's said. Here is what we have, right? Concatenate them together, we have 160 bits. All right. So simply concatenate the H values here together, we have it. All right. So that is what we have for the SHA-1. Let me close this one so we can see it. So let me close the details so we don't want to see too much, right? So now here, the algorithm I implemented has an option for displaying the intermediate results, just in case we want to verify the intermediate results. So for example, here we have the message is ABC, then the digest is here, right? So we simply have the algorithm here, and then the digest is here. But if I want to show the intermediate result, then I simply show the intermediate results by saying that I want to display the intermediate result. Then it will show me all of the intermediate result. Okay. Like, okay, so here are the original variables. I mean, the original message. And what happened after I appended the the values, and then what are the intermediate results for the H values, right? So finally, we have the H values are here. Combine them together, we have the final results. So once we have our algorithm, then we can modify the program a little bit to have our own hashing function. Okay, so as I mentioned before, yeah, here we have the initial values for k, right? And then we have the initial value for h, right? So if we change the values here to what we want, then we have our own hashing function. Okay, let's see how we have it. Okay, so here is what I have for randomly generated value. Okay, so for example, we want to have the initial values for the hash values for the hash table randomly generated. And here you can see that I have the one well distributed along the string. Okay, then we can choose that one. We can choose that one. Okay, so let's say I want to generate a randomly generated values for the H. Okay, that has 32 bits. Here is for SHA-1. So if it's for SHA-2 or SHA-3, then I simply change this one to 64. Then I will have a randomly generated hash value to initialize the algorithm. Okay? So the second time I run it, I will have a different value. Okay. Right? So every time when I run my function, I will have a different values because I use the random function here. Okay. All right. So that's it. We can have our own hash value, right? Then it's the first step that every Bitcoin or every digital coin platform would like to do. Okay, they have their own hashing function, and of course they also have their say encryption algorithm. But encryption, they basically have to follow the RSA template. Okay, then we can. I will show you how we can do it for the encryption a little bit later. Okay, so that is the algorithm for the SHA. Okay, for the hashing. All right, and now that is the SHA-1, where we have computers with with the works of 32 bits. But nowadays we know that almost all of the computer will have works in 64 bits. So that's why we want to change it to the new SHA, right? We call SHA-2, including SHA-256 or SHA-512. That is the most popular now. Yeah, but the algorithm is exactly the same, except that we have to extend the length of the digest. Excuse me. Okay, so same thing. Okay, exactly the same, but we change it a little bit. Okay, instead of 512, we have 1024 bits, right? And then the length. Previously we used 64, but now we use twice 128 bits for the length. Okay, when we append. And then we have the initial value is not 160 bits, but it's 512. Okay, that said, okay, so here's what we have: padding, and then add the length by the end. So same thing, manipulation. Previously, for the SHA-1, we see that we just usually 5 words from A to E, right? That is for 160 bits. Now we want to add 3 more, okay? So we want to add 3 more. Actually, this one is time 2. Remember that in the previous SHA-1, we have 5 words. Each word has the length of 32, which is 160, right? Here we have also 5 words, but with the length of 64, so we have 312, right? And then we add 3 more words of 64, so we have 512 words. And then how to manipulate the words? So we have the function here, function there, and then function here. Okay. So again, the functions we have here will be just not and or of manipulating the values here, right? Adding we use in SHA-1, all right? Okay, so we have all of that. So it's very similar, and again, we do 80 rounds. Yeah, we do 80 rounds. And the functions are a little bit different, but basically the same idea. Okay, not and all, and then rotation, right? Rotation 28 bit, and then 34 bit. Yeah. All right, so that is the SHA function. Okay, so hashing is pretty straightforward, right? Any question about the hashing? No question, right? The best thing to learn is to implement the algorithm. Okay, if you have time, okay, so it's the holiday season. If you want, you can implement the hashing algorithm here. And I will also show you how to understand and implement the encryption, right? And the next step is, okay, we have hashing, we have encryption, maybe not yet encryption. I will talk about encryption a little bit. But right now, the question is, how can we use hashing for Bitcoin? Okay, is anything in common? So we know and we heard a lot about coins, digital coins, right? Bitcoin, Ethereum, and then say Binance. Okay, so they say that hashing and encryption are the foundations for any of such digital coin. So what are they? So we will try to see how we use the hashing and the encryption for creating our own coin, right? So we can create our own coin, of course. But let's see how it works with Bitcoin first. Okay, so the idea, as I mentioned before, is that we have a distributed, decentralized digital currency. It means that no bank will control about the coin, right? And then there's no inflation. Okay? You cannot simply print the bills, right? Like, okay, so I mean, the government think that we need more money for the economy to give out to the people. They simply print new money, right? But for Bitcoins, it's impossible. You cannot simply print out the money, the coins. Okay, there must be some restriction for doing so that we will see. Okay, why we say that Bitcoins is decentralized, meaning that no bank can have the let's say control over that. No government can control over that, and then no one can simply produce the coin if they want. It's impossible. Okay, and then I mean the idea was given by Nakamoto in 2008. By the way, I posted his Bitcoin paper on Moodle. Have you had a look at that? Read it, and you will understand more. Okay. Okay. So maybe during the break, okay, if you have time, just read it. I think about 5-6 pages, not much, right? But it will summarize what his idea was. Okay. I mean, we don't know if it's a male or female person yet. Okay. But anyway, the idea was very nice. Okay. And then we have digital check, right? Let's say how it works as a digital check. All right, so here's the paper I posted on Moodle, right? The idea was to allow online payment to be sent directly from one party to another without going through any bank, okay? How can we do that? How can we guarantee that the money actually come from the first one to the second one, right? And also, how can we prevent what we call the double spending? Okay, like, okay, I have $100, right? I send the payment simultaneously to Best Buy and to Amazon to buy something. Is it possible? Can I do that? Right? Technically, of course, I mean, morally should not do that, right? But technically, if someone tried to cheat, they will send two checks, right? At the same time. And of course, just only one of them can withdraw the money because I have $100, right? Okay, so how can we prevent that situation? Okay. Of course, we can prevent that. Otherwise, there will be no Bitcoins, right? So here's the idea. So what is a blockchain? Okay. We know that Bitcoins and all of the other coins are based upon what we call the blockchain. So what is a blockchain? A blockchain is simply a linked list or a chain of blocks. Yeah, is that simple? Yeah, it's very simple, right? Okay, so here we have a chain of blocks. Yeah, each of the block here we have some information. Okay, so like here in one block we have the transaction, like Alice pay Bob 3 Bitcoins, right? And Chris pay Doris 2 Bitcoins, right? And then the person who create the block will have 25 Bitcoins reward to them because they created this block, all right? And here, inside this block, we have the ID. The ID can be the block ID, okay? So every block will be ID'd by a number. And then inside that, we have a pointer to the previous block. And then, of course, another pointer to the next block, right? So a few questions here. We say that the system is safe because in this current block, we have the hash value of the previous one. So the previous block here will be hashed using, for example, the SHA algorithm and have the hash value here. Okay? So everybody knows all of the blocks. Is it safe? Let's say here is the current block, right? After Alice pays bought 3 bitcoins, because Alice see the block here, she has a copy of this block. So is it possible for her, after 1 or 2 days, go back here and change this one to 1 bitcoin? 1 bitcoin now is about 17,000, right? So she removed 2 bitcoins, means that she has immediately, say, $34,000. Is it possible? Number one, okay, number one, here in this situation, it's impossible, regardless of what other people are saying, because when she changed this one, then everybody can verify that once they hash the new block, it will not match with the hash value they have before in the next block, right? Okay, so that said, if one person change, it does not match. Okay, so that is the problem. Okay? Later on, we will talk about the situation in the when we have a conflict, right? And then who will decide whether or not that conflict is legitimate? And in that situation, we have the consensus. Okay? But here we don't need to have the consensus. Clearly, this block is not legitimate. So nobody will accept that, right? So that said, hashing is very important for blockchains because we use the hash value of this block, store it here for the next one. So if anyone change, then there's a mismatch, meaning that this block, copy of this block is not legitimate. Okay? So that's why hashing is very important. All right. Okay, so here we have a linked list, and then every time we have new transactions, right? And then a new block will be added. But who can add the new block? Everybody can add, right? So there's a competition there. But who will finally have the reward? Meaning that everybody want to add a new block because if you can add a new block, you have some reward. Like you have 1 Bitcoin, for example, and that is a lot of money. Okay, so there's a competition. So who will decide who won the competition? So basically, there must be some proof of work, right? And then the one who can solve the problem earliest. So let's say I will be the first one to solve the problem. That what problem I will mention a little bit later, right? But there is a problem that everybody will try to solve, and then the first one who can solve the problem will have the power to add the next block. Okay. Now, before we move forward, I will show you one thing. Okay, that is here we have the blockchains or chain of blocks or list of blocks or linked list of blocks. Okay, but what are the blocks looks like? Let's see how they look like. Okay, so here is the one, say, platform, and here we have a lot of different values like bitcoins, and then we have Ethereum, etc. But let's see what we have for bitcoins right now. So you can see here that we have the blockchains, right? Which is a chain of blocks, and the values here are current. Okay? Right now is what happened on the world. And then you can see that each of the block will have the block ID, right? The latest one is here. So we have the block ID of 764,324, right? So here we have the hash. We have the hash of the previous block, right? And then we have the values, and then we have all of the transactions. Okay, each of the transaction will be here, right? From whom to whom, right? How many Bitcoin, etc. Okay, so that said, we have all of the information in one block, right? Okay, and then you can also see here the nonce. Okay, the nonce value is here. Okay, we will talk a little bit about the nonce. What does it mean? Okay, the nonce here is basically the solution that the person who added the block here finished it in the earliest time. Okay, and then you can also see that okay, so here we have this block, right? Now, this block is added by one platform, and you can see that each different blocks, we have almost a different person or group that won the right to add the block in. So for example, this one was added by the Ann Poon. The next one was added by unknown, meaning that they don't want to show who they are. Okay. Ann Poon, and then we have here also Ann Poon, right? Okay. Yeah, BTC platform, right? Bitcoin platform. Okay. So that said is what we have for the blockchains. Okay, so what is a blockchain? It's a chain of blocks, right? Why hashing is important? Because hashing provides a efficient meaning for, say, securing the, say, legitimacy of the blocks or all of the blocks. Okay. Okay, so we already see this, right? Okay. Now, the next step would be about how to guarantee that. Okay. Let's say Alice wants to send some money to Bob. How we know that it's actually Alice? Okay. Of course, we don't have the name, the driver license number, anything. Okay. Each person will have what they call the public key. Okay. Every person can generate their own identity. Okay. It's what we call the public key. Okay. I will show you how to generate our own public key and how to generate our own signature. Now, if you search Google, you can see that there are many websites that can give you your signature, so you can use it for signing some paperwork, right? And then some platform like Bitcoin or FTX, they will generate the public key for you. But in fact, we can do it by ourselves. Okay, we are computer scientists, so we can do it by ourselves by just writing a simple program and then generate all of such information. Of course, not for ourselves, but if we want, we can open a new platform and then provide the service. Okay, so that's it. How do we know that? So let's say I want to buy something, right? And meaning that I want to send the money to that person. And on the other hand, that person would like to expect the payment from myself, right? So that said, first we want to know for sure that the person I send money to will receive it, right? And not something impersonate that buyer or that seller. For example, if I want to buy something from Best Buy, I want to be sure that the person who received my payment is real Best Buy, not someone who just take my money and will not send anything to me, right? So that said, how can we assure that the person I send money to is the one I actually want to send the money to? And here we have what we call the public and private key pair. So this one is not new. It was invented in, I think, 1973 or so. It's what we call RSA algorithm. Okay. All right. So here's the idea. All right. So everybody can generate a pair of keys or ID for themselves. Yeah. Let's say we want to have a very large number, and that large number will be used for computing the public key and the private key. Okay. Public key means that I will send it out to everybody, saying that here's my ID. Okay, like here, right? This public key is made available, for example, on my email or on my website. I will say that, hey, here's my public key, or in other words, here's my ID. Okay. Obviously, the first thing you observe is that I can have multiple IDs, right? And nobody knows it's me, right? So that said, on the internet, everybody can remain anonymous, and you can have multiple IDs. Okay, that is possible, right? And now I will have the second key that I keep for myself. It's called the private key. Okay? I choose the private key for decrypting the messages when I receive it from somebody else. Okay? So the idea is that I want to receive a message from Alice. Okay? So I am Bob, okay? And I want to receive a message from Alice. So I don't want everybody to see the message because the message can be, let's say, she sent me the ID of the Bitcoin, right? Or in other words, the ID number of her wallet. Okay, so everybody has a Bitcoin, and in the wallet they have the ID for each of the Bitcoin. All right, so she will send me that information. That said, that information is expected for only me because if everybody know, then they can use it, right? So that said, Alice will use my public key to encrypt it, meaning after she uses my public key, the information will be encrypted. And nobody can understand the message except me when I use my private key to decrypt it. And after I decrypt that, I can see the original message. Okay? So this one is what we call public private key or RSA algorithm. I think it's Rivest, Sharma, and the last one I forgot the name. Okay. All right. So let's see how it works. Again, I have implemented the idea here. Okay. So I will generate the key using the function RSA. Okay, the function RSA is very simple. I will pick two big prime numbers, okay? Multiply them together, right? And then we'll try to generate the public and the private key from here. So here is a simple example. I just want to have a not very big numbers because it was fast enough for me to show you. Yeah? Of course, if I want to generate my own public-private key, I will have a much longer key. Okay. In that situation, nobody can find out what is my key, right? So here I have two. I will give out two values for everybody. It's called the public key. Yeah. Here is the number, and that will be the number after I multiply the two prime values together, right? And then here is the public key, right? I will give out this information. And at the same time, I have my private key here, okay? The same number n, and then here is the private key. So in other words, the program here will give me my key that has three information. The origin number I use for generating the key, the public key and the private key. Okay. So once I have the public key, I can encrypt that, or everybody can encrypt that. For example, here, I have the message is computer science, right? I want to use my public key here to encrypt that. So that said, here is my, oops, I have to run it again. Okay. So if I choose the public key here, I can encrypt that. And after I encrypt that, I have the results here, right? So now nobody can understand this message except myself when I have my private key. Okay, so I can use my private key and then decrypt that. I have the original message again. Okay, so that said, I will give out the public key. Everybody can see the public key and they can use the public key to encrypt the message they want to send to me. Okay, and only me with my private key can decrypt the message. All right. The good thing about the public private key is that we can go both ways. Okay, what does it mean with going both ways? So we can have the forward encryption. Forward encryption means that I can encrypt by using public key and decrypt by using private key. Or I can encrypt by private key and decrypt by public key. Yeah, so that is the reason why I say that for the public private keys, we can go both ways. Yeah. Why we need that both way, you will see. Okay? Because we need that for the blockchains and also for the bitcoins. All right. Okay, so that is what we have for public and private key. And by the way, I think you took calculus 1 and 2, and apparently, did you take any class on combinatory? Okay, that's fine. I mean, if you like, then I can show you the correctness proof. But correctness proof of this algorithm is not simple. So that's why usually only students who finish not only calculus but also combinatorics will understand the proof. The proof is not simple; is quite involved. But right now we just see the algorithm, right? And then correctness of the algorithm is not simple, but we can prove that. Okay, so now I will stop here. But by the way, on the slides here, I updated on Moodle, right? And one thing I want you to do is that, okay, so you understand about hashing, you understand about public-private key, right? And then another thing we want to do is that how can we have our signature? What does it mean with signature? I think I have here, okay? I have a picture here. So you have a check, right? Here is the person who write the check. Here's the person who pay. And here's the signature. Okay. What does it mean with using public key and private key? Okay. Here is easy, public key, right? But how can we have the signature, right? It's what we will learn after the break. All right. By the way, any question about the homework assignment? I think it should not be difficult for all of you, right? No question. Okay. But if you have any question, don't hesitate to contact me, right? But oh yeah, okay. Good, Caleb. You did very well. Okay. All right. Otherwise, have a good Thanksgiving, and I'll see you after the Thanksgiving. Okay, take care. Bye bye.